Picture this. It's February 2021. You are in Oklahoma.
Oh, man. Yeah, that was a wild time.
Right. Outside, the temperature has just plummeted to historic negative single digits. The wind is howling. There's frost creeping up the inside of the window panes.
That's absolute brutal weather for that area.
Exactly. And your neighborhood is dead quiet, except for the hum of heating systems that are just desperately fighting the freeze.
Yeah, which is a true stress test for any piece of machinery, really.
It is. Now, imagine you're a master HVAC technician operating a shop in a town like, say, Kingfisher. Your phone starts ringing off the hook.
Oh, I can only imagine the absolute chaos for those technicians.
It was crazy. Half the calls coming into the shop are because traditional gas furnaces have completely died.
Right.
But the other half of the callers are in an absolute panic because they have a heat pump and they are utterly convinced it's failing. They think the technology, just simply cannot handle the cold.
Well, and here's the paradox we were exploring today, right? Most of those heat pumps were actually doing just fine.
Wait, really?
Yeah. Which is a totally counterintuitive reality for so many homeowners.
Right.
I mean, we have this deeply ingrained, almost generational belief about what a heating system should look, sound, and feel like when it's working properly.
Especially in extreme weather, yeah. But wait, if the machines were doing exactly what they were engineered to do, why were the phone lines melting down?
Right. Well, to answer that, we have to look at the actual physics, the economics, and really the behavioral psychology of modern heat pumps.
And luckily, we have a fascinating breakdown to help us do just that. Our source material today is an interview with Dave Hartzell, a master HVAC technician with 45 years in the trade down in Oklahoma.
And Oklahoma is famous for those wild temperature swings, mild winters one week and historic subzero disasters the next.
Exactly. So our mission for this deep dive is to cut right through the neighborhood gossip. We want you to be able to look at the actual facts so you can make an informed decision for your own home's climate control.
Because there's a lot of misinformation out there.
There really is. Okay, let's unpack this. To understand the sheer panic from those homeowners, we have to start with the history, right?
Yeah, we have to look at why your neighbors, or maybe even your parents, are convinced that heat pumps are, practically useless the second there is frost on the ground.
Because that reputation didn't just come out of nowhere.
No, not at all. It stems from the 30-degree rule, which, to be fair, wasn't actually a myth if you go back a few decades.
So this is an outdated reputation that just somehow stuck around. What was physically happening in those older units?
Well, back in the 1980s, heat pumps relied on single-stage compressors and very basic refrigerants. They were binary machines.
Meaning they were just on or off.
Exactly. They were either running at 100% capacity or they were completely off.
Okay, I see.
So when the outdoor temperature dropped below roughly 30 degrees Fahrenheit, those 80s compressors simply couldn't maintain the pressure required to extract heat from the freezing air. They essentially just gave up.
Wow. But if the compressor gives up at 30 degrees, the house is going to freeze. There had to be a backup mechanism, right?
Oh, there was. It was called auxiliary electric heat, or strip heat.
Strip heat.
Yeah. When the compressor failed, the system automatically switched over to electric resistance coils. It's essentially the exact same technology as the glowing wires inside a toaster.
Oh, geez. That sounds expensive.
It kept the house warm, sure, but the electrical draw was astronomical. Your power bill would just skyrocket overnight.
So it makes total sense why people would conclude that the technology was a massive liability in the winter.
Right. It makes perfect sense for 1985. But the engineering has completely changed since then. Modern heat pumps use variable speed inverter compressors.
Okay, so how is that different from the old binary ones?
Instead of just turning on or off, these modern compressors can continuously adjust their speed. They dial their output up or down precisely to match the heating demand of the house.
So they aren't just blasting at 100% all the time.
Exactly. They draw far less power while continuously moving heat. But, the compressor is really only half the equation here.
Right. The other half is the modern refrigerant flowing through those pipes. Let's talk about the physics of that, because this is where I think people get really tripped up.
Oh, for sure.
How does a machine extract heat from air that is 5 degrees Fahrenheit to a human being that feels completely devoid of heat?
I know it sounds like magic, but think of it like wringing moisture out of a slightly damp sponge.
Okay, a damp sponge. I'm with you.
If you touch a damp sponge, it might not feel wet to your hand, right?
Yeah.
But if you apply enough mechanical force, like if you squeeze it really hard, water will still drip out.
Oh, I see where you're going with this.
The air outside is the sponge. Even at 5 degrees Fahrenheit, the air contains a significant amount of thermal energy. And modern refrigerants are chemically designed with boiling points around minus 50 degrees Fahrenheit.
Wait, minus 50. So to the refrigerant, 5-degree air is actually boiling hot.
Exactly. When that incredibly cold liquid refrigerant is exposed to 5-degree outdoor air, it absorbs that ambient thermal energy and boils into a gas.
Okay, wow.
The compressor then takes that gas and squeezes it, just like the sponge. When you compress a gas, its temperature rises dramatically.
And then that concentrated high-temperature heat is pushed inside your home. That is brilliant.
It really is. And the Department of Energy data backs up how effective this phase change process is.
Yeah, the stats are wild.
Wow.
Modern cold climate heat pumps like the Mitsubishi Hyperheat or those newer variable speed trains, they maintain highly efficient operation down to 5 degrees Fahrenheit.
Right. They don't just survive, they are efficient.
In fact, some of those Mitsubishi units are rated to operate at their full heating capacity at 5 degrees, and they continue operating effectively all the way down to minus 13 degrees Fahrenheit.
Minus 13. I mean, they are mechanically thriving in environments where older units would have just shut down completely.
Which brings us to the core metric of the entire HVAC industry, right? The COP, or coefficient of performance.
Yes, COP. Let's break that down, because this seems to be the mathematical proof of why the technology is taking over.
Right.
To really grasp COP, you have to look at the ceiling for traditional electric heating. Those emergency toaster coils we talked about, or a standard electric baseboard heater, they have a COP of exactly 1.
Meaning 1 unit of electricity consumed yields exactly 1 unit of heat output.
Yes. That is the absolute physical limit of resistance heating. You simply cannot generate more heat than the electrical energy you consume.
But heat pumps don't generate heat out of nothing. They just move it.
Exactly. Because transferring existing thermal energy is mechanically much easier than creating it, a heat pump in moderate weather boasts a COP of 3 or even 4.
Wow, so you were getting 3 to 4 units of heat for every 1 unit of electricity you pay for.
Yes.
Okay, so a traditional furnace or a baseboard heater is essentially like chopping wood and burning it to get warm. You have to expend a massive amount of energy to create the fire.
That's a great analogy.
But a heat pump is like paying a delivery driver to move pre-cut wood into your house. It is always going to be cheaper to pay for the movement rather than the creation of the heat.
Exactly. That is the fundamental economic advantage right there. Even in that freezing 5-degree weather we discussed, modern cold climate units maintain a COP above 2.
So even when the machine is working its hardest in the bitter cold, it is still twice as efficient as a traditional electric heater.
Yes.
Ugh.
But there is a strange discrepancy with the Department of Energy statistics here.
Oh, right. I wanted to ask about that. If heat pumps are moving heat with a COP of 3 or 4, why does the DOE state that they only cut heating energy use by about 50% compared to a gas furnace, but up to 75% compared to baseboard electric?
Yeah, it seems weird, right? If the machine is that efficient, shouldn't the savings be uniform?
Exactly. What's going on there?
Well, what's fascinating here is the difference between electrical draw and combustion efficiency. A gas furnace is not using electricity to create heat. It is burning a combustible fossil fuel.
Okay, right.
And modern gas furnaces are incredibly efficient at that specific task, often converting like 90 to 95% of that natural gas directly into usable heat.
So when you compare a heat pump to a gas furnace, you are comparing the cost of moving heat electrically versus the cost of burning gas efficiently.
Right. That is why the energy savings sit around 50%. But when comparing a heat pump to baseboard electric heating, which is a pure one-to-one electrical draw, the heat pump's ability to move 3 or 4 units of heat per unit of electricity result in that massive 75% reduction.
Okay, so it's really an apples to oranges comparison of fuel types. That makes sense.
Totally.
But this brings us back to Oklahoma. If the underlying physics and the COP math prove that modern units easily extract heat at 5 degrees, the panic calls to the HVAC technicians during that freeze just don't make sense mechanically.
No, they don't.
So it was actually failing.
Honestly. The machinery wasn't failing. It was the homeowner's psychology.
Psychology, really.
Yeah. During that freeze, the panic calls usually came down to 3 specific scenarios. The first one was legitimate. The unit was genuinely an ancient 1990s model that just couldn't handle the load.
Sure, okay. Old tech.
Right. The second scenario was a silent failure. The homeowner had a modern heat pump, but their backup electric strip had broken months prior without them knowing.
Oh, no. So they had no safety net when the temperature dropped to historic lows.
Exactly. but both of those are mechanical issues. The third scenario is the psychological failure.
Okay, tell me about that.
This was the most common scenario, actually. Homeowners heard their system running continuously, without stopping, for days on end.
And because we are all so conditioned by the sound of old furnaces, they automatically assumed a constantly running machine was a broken machine.
Exactly. This is a major behavioral gap we have to cross. Furnaces are designed to be sprinters.
Right, they kick on, blast the house with aggressive, intense heat for like 10 minutes, shut off, and then the house slowly cools down until the cycle repeats.
Yeah. But heat pumps are marathon runners. They are engineered to run slowly and steadily.
Because of those variable speed compressors you mentioned.
Right. They can ramp down their effort to quietly sip electricity, continuously circulating air to maintain a perfectly even temperature. They eliminate those wild thermostat swings of a furnace.
Creating a much more stable environment. But here's where it gets really interesting. Because the physical sensation of that air creates a sensory mismatch.
Oh, absolutely.
A traditional gas furnace blasts air out of the vents at an incredibly hot 130 to 140 degrees Fahrenheit. A heat pump, however, delivers air between like 95 and 105 degrees.
Which completely alters the sensory experience of standing in your home.
Yeah. I mean, because the air blowing out of the vent is literally a few degrees cooler than normal human skin temperature, it doesn't trigger that comforting sensation of warming up.
No, it doesn't.
In a cold house, 95-degree air might even feel like a slight draft. So how does a machine physically heat a living room if the air it produces doesn't even feel warm to the touch?
Right, it's a great question. It really comes down to ambient heating versus directional radiant heating. The ambient temperature of your living room is likely sitting around, say, 68 or 70 degrees.
Okay.
If you continuously pump 95-degree air into a 68-degree space, the laws of thermodynamics dictate that the room will warm up and maintain that temperature.
It just doesn't feel like you were standing in front of a fireplace while it happens.
Precisely. It requires a total mental reset. You just have to stop treating your floor registers like a campfire to warm your hands over.
Yeah, you have to trust that the constant invisible circulation is actually elevating the ambient temperature of the entire structure.
Right. But, changing our sensory expectations is one hurdle. The reality is an air source heat pump still has to work incredibly hard to wring that thermal energy out of 5-degree air.
Yeah, that's a lot of work for the compressor. Is there a way to just bypass the volatile outside weather entirely?
There actually is, and it is considered the gold standard for cold weather climate control. We're talking about geothermal heat pumps, like the Climate Master GeoLead systems.
Ah, geothermal. So instead of placing a metal box in the backyard to battle the blizzard, a geothermal system buries a network of pipes deep underground.
Exactly. The Earth basically acts as a massive thermal battery. Just a few feet below the surface, the ground stays at a remarkably constant temperature of about 55 degrees Fahrenheit.
Wow, 55 degrees year-round?
Yep, regardless of whether there is a historic freeze or a blistering heat wave up above.
So the heat pump never even interacts with the winter air. As far as the machine is concerned, it is continually pulling heat from a pleasant 55-degree spring day.
Right. And because it operates in such a mild, stable environment, a geothermal system provides the lowest operating costs of any heat source on the market.
That makes total sense.
It also boasts the longest lifespan because the compressor isn't subjected to the extreme physical stress of freezing weather.
Okay, the engineering is brilliant, but the financial barrier is massive. I mean, a standard air source heat pump might cost anywhere from $8,000 to $14,000 to install.
True.
But a full geothermal installation requires heavy excavation and drilling, pushing the cost to between $20,000 and $30,000. That is a steep premium just to avoid the winter air. So, what does this all mean for my wallet? Because 30 grand is a tough pill to swallow.
It is, but if we connect this to the bigger picture, the map starts to shift significantly when you look at the current rebate landscape.
Yeah.
We are in a really unique transitional period right now in 2026.
Right, because the federal incentives changed recently.
They did. The federal 25D tax credit, which offered a 30% reduction and was, frankly, a major driver for geothermal adoption, officially expired on December 31st, 2025.
Wait, so there is no federal credit for installs happening right now? That seems like it would kill the geothermal market overnight.
You'd think so, but it actually didn't. Local utility companies have stepped in to fill that void.
Really? Why would they do that?
Utilities recognize that geothermal systems dramatically reduce the strain on the electrical grid during peak winter freezes.
Yeah.
So in places like Oklahoma, the local rebates are currently massive.
Okay, how massive are we talking?
Well, OG&E is offering $1,000 per ton of capacity. And a local cooperative called Seek Energy is offering $2,000 per ton.
A typical residential home requires anywhere from what, a 2 to a 5-ton system?
Exactly.
So depending on your specific utility territory, you could be looking at a direct rebate of $4,000 to $10,000, or even up to $12,000 in some cooperative territories.
Yep. That local money effectively neutralizes the loss of the federal tax credit. It brings the net cost of geothermal much closer to a high-end air source system.
Wow. Okay, so it changes the decision from a purely upfront sticker shock to a long-term life cycle calculation.
It really does.
So factoring in those massive local rebates, how does someone sitting in their living room right now actually build a decision matrix for their own home? How do you choose what to buy?
Well, the logic flows through a very specific sequence. The very first data point you need to establish is your current infrastructure. Like, do you already have a natural gas line running to your house? And is your current gas furnace still relatively new?
And if the answer is yes.
If it's yes, the most financially sound advice is usually to just keep the gas furnace. Natural gas is relatively cheap in many parts of the country.
Okay.
You could just upgrade your air conditioner to a hybrid heat pump. You let the heat pump handle the mild fall and spring weather with incredible efficiency, and then let the gas furnace take over when the historic freeze hits.
That sounds like a highly practical middle ground.
It is. But if you do not have a gas line, or your entire HVAC system is decades old and failing, an air source heat pump is mathematically the winning choice over propane or traditional electric resistance heating.
Especially considering utilities like OGN are also offering a $1,500 rebate specifically for high-efficiency air source heat pumps. The financial incentives are heavily weighted toward making the switch.
Absolutely. However, once you decide to install a heat pump, you face the single most critical hurdle in the entire process,
Which is?
determining the size of the unit.
Let's talk about sizing, because naturally, if I'm spending thousands of dollars on a brand new, highly efficient system, shouldn't I just buy the largest capacity unit I can comfortably afford?
Uh-oh.
It's like buying a truck, right? You buy the V8 engine so you have the towing power if you ever need it, even if you just drive to the grocery store most days. Why wouldn't you want surplus power in a heating system?
Well, this raises an important question, and it highlights a dangerous misconception that leads to, frankly, miserable living conditions.
Really?
Yes. A heat pump is not a truck. Oversizing a heat pump is catastrophic for your home's comfort, largely due to how these machines handle humidity in the summer.
Okay, what happens when the machine is too powerful for the square footage?
If you put a massive, oversized system in a moderately sized house, it will alter the temperature far too quickly. It will blast the house with cold air, hit the target temperature on the thermostat in 5 or 10 minutes, and immediately shut down.
And that rapid starting and stopping is called short cycling, right?
Exactly.
But why does short cycling affect the humidity?
Because an air conditioner needs to run continuously for a sustained period of time to actively pull moisture out of the air. If the machine short cycles, it drops the air temperature without removing the water vapor.
Oh, yuck. So your house will feel like a cold, damp cave.
Yes, exactly. Furthermore, the constant starting and stopping destroys the efficiency of the inverter compressor and drastically shortens the lifespan of the machinery.
Wow. Okay, but conversely, undersizing the unit is just as bad, right?
Oh, absolutely.
Because if the machine lacks the capacity to handle the cubic footage of the home, it will constantly fall behind during a freeze. And that forces the system to rely on those wildly expensive auxiliary electric strips we discussed earlier.
Right, so you need a system that fits the precise thermal dynamics of your house. And you do not get that precision by letting a contractor simply eyeball the property or, by blindly matching the tonnage of the old system they are removing from your basement.
What's the alternative?
You have to demand a manual J-load calculation.
A manual J. Okay, what exactly is the software calculating that makes it so much better than an experienced technician's educated guess?
Well, a manual J calculation builds a comprehensive mathematical thermal model of your specific home.
Okay.
It factors in your total square footage, the height of your ceilings, the specific R value of the insulation in your attic and walls, the number and quality of your windows, the direction your house faces relative to the sun.
Wow, it gets that specific.
Oh, yeah. It even factors in the historical climate data for your exact zip code. It calculates the exact amount of thermal energy your home loses in the winter and gains in the summer.
That is incredible.
Without a manual J, you are basically gambling thousands of dollars on a guess.
So, if you take nothing else away from this deep dive, write down manual J and keep it ready for the next time an HVAC contractor gives you a quote. It is your ultimate shield against a disastrous installation.
100%.
Well, we started out trying to separate the neighborhood gossip from the actual science of modern climate control, and we found that the gossip is heavily anchored in the single-stage compressors of the 1980s.
Right, that 30-degree rule simply does not apply to modern inverter technology and refrigerants that boil at minus 50 degrees.
We unpacked the COP math, proving that moving heat is fundamentally cheaper than creating it. We explored the geothermal option that completely bypasses the winter air.
And we navigated the transition from federal tax credits to massive local utility rebates here in 2026.
Most importantly, I think, we uncovered the behavioral psychology of the thermostat. We learned why the marathon running nature of a heat pump and the neutral sensation of 95-degree air requires a complete reset of our expectations.
It really is a mental shift for homeowners.
It is. So if you are currently staring down a failing furnace or you simply want to future-proof your utility bills against the next big freeze, you now have the blueprint.
You really do.
You know to check your local cooperative for rebates, you know to demand a manual J calculation, and you know not to panic when your outdoor unit hums continuously through a winter storm.
It's just doing its job.
Exactly. It makes you wonder, though, if we are entirely moving away from the fire mentality of blasting 140-degree air out of a floor vent, how long until floor plans and home architecture start changing to match this new invisible climate control?
Oh, that is a fascinating trajectory to think about.
Right?
When the primary heat source becomes a slow, ambient, and highly dispersed circulation rather than an aggressive, localized blast, the need to huddle furniture near registers or design living spaces around central thermal hubs disappears entirely.
As the machinery evolves from a sprinter to a marathon runner, the very way we live inside our walls is bound to evolve right alongside it. Well, thank you for going on this deep dive with us.
It was a pleasure.
And remember, the next time the temperature plummets and the neighborhood goes quiet, that humming box in your backyard isn't struggling. It is just pacing itself. Keep learning, and we will see you next time.